Uh, Hope all of you can see the screen. I have shared my PPT. Just a second. So all of you can see the PPT. Hopefully, you draw my attention. You can stop me, or you can draw my attention writing in the chat box so that I can address your queries or any trouble you face in between. So let us start today's session, and I welcome you all in the afternoon session. So today's topic is actually I have made various topic. So in that mainly concerned about PWM, I will be discussing PWM current controllers. Okay, first of all, you can hear me clearly. I need to check your side. Is it clear? Can you just respond? My voice is clear, reaching to you. Can you just write in the chat box? Okay, and you can see the PPT, the slideshow clearly. I hope it is changing. Okay, okay, it's okay. Now, yes, it is changing. Okay, so these are the content for today's lecture. So the content is distributed like this. So what is PWM current controller? So first I will be talking about current controllers and the PWM current controllers, where you will be dealing with some switching technique, and that switching technique is considered to be a high switching. Okay, not to be switched at very low frequency. And generally, when you say low frequency switching, we call one switching in fundamental cycle or two switching in a fundamental cycle. But when you go more than that, maybe more than 10 switching fundamental cycle or more than that, we call it a high switching devices. And then we deal with this PWM techniques, pulse width modulation technique, and the basic of the pulse width modulation technique. Hopefully, everybody should have the background here as the audience or participants. So I am not going into the much detail of the basic of the PWM techniques, but I expect all of you should know. And so based upon that, so the PWM current controller will be discussed. Some of the features of the different types of current controllers, so classifications of current controllers, I'll be talking about in the next point. So the basic, the structure of this presentation would be, the main idea of this presentation would be to give you some flavor of the present, what are the different topics are available, what are the different kind controllers are available, so that you can start your research if you want to. So you can take few points, important points from this discussion, and I'll give you a lot of references so that you will get some idea from where to start your research in your for your career. So basically, I don't know how much time will be. It will take some time to explain each and every fundamental things. but I'll skip some of the fundamental discussions. So just give you some of the ideas, overall ideas, so that you, and further if you require some explanation, definitely I'll come back to that. So next will, as a third point, the salient points of different control techniques, current control techniques basically. So I'll be discussing some of the internal details of the current controller, some merits and demerits of each one of these techniques. Then the discussion on space vector PWM and sinusoidal pulse width modulation techniques. So thereby I'll be discussing the DC bus utilization, how to increase the utilization of the DC bus of the existing DC bus of any converter system, where you either have DC to AC or AC to DC conversion. Then I'll be talking about some multi-level inverters, why multi-level inverters is required and what are the advantages of it. Although you know some part of the multi-level inverters, but I will be talking little bit details on this. And obviously my focus will be on restricted to three-level multi-level inverter topologies. So salient points of different three-level converter topologies also will be shown in this discussion, and also some of the flavor of the future research, how it is going on. So you'll get a small glimpse of that. Okay, so let us try to get into the main topic. What is what is a current controller, PWM current controller? Okay, so basically you see. Basically, you see a structure like this in almost all the power supply system. So suppose you are having an induction motor drive. So you draw the power from some three-phase available power supply. So you need a isolation for several reasons, or you need a protection, you need a electrical isolation, you need to have some common mode noise elimination. So for several reasons you need isolation. So that's what this transformer is coming just after the three-phase supply, and you need to do a rectification that is required to get a DC link, and that DC link is fed through that DC link. Actually, you are feeding a IGBT based PWM voltage source inverter, and then you can control as per your wish. Okay, and you can get any output at the terminals of the inverter when you have a DC link. So that then you are completely decoupled with the three-phase power supply at the input side, and or any noise is coming in the three-phase power supply, that generally does not pass through this DC link, because you have a capacitor that eliminates the noise, high frequency noises which is coming from the input side. So that is a very unique structure and well used, when conventionally used structure power supply as a power supply, which is feeding to a induction motor. Here we are showing an induction motor. It can be any type of motors. So when you're driving a motor, so very essentially you require a control, and most of the time you cannot depend on voltage source control, right? So you need to have a current reference, and you want to track that current reference, and how that current reference is generated, and these are the different area depending on your application, whether you want to have a torque control, whether you want to follow a particular power or reactive power reference, or you want to follow some speed. So from those outer layer control, you generally find out a current reference. So those are the outer layer control. I am not showing here. So basically you get a current reference as a result out of those outer layer control. So inner layer, so basically inner layer, I want to mean that inside the which is very near to the switches, the gating pulse to generate the gating pulse, you require a current reference. Okay, so that current reference requires a current controller strategy, so that you can appropriately switch on the switches which are in a particular fashion, okay, in order to get a current at the line which will be following the reference current. Okay, so if you look at this So this is not only this induction motor. This is actually shown as induction motor, but actually it can be a grid also. If you would like to see in place of a induction motor, you can connect a grid. So most of the things will remain as it is, except the three-phase power supply. It can be replaced by a solar converter, where this automatically DC link is provided. Okay. So, but at the inverter side, your control will not change as such. So the strategy will remain same. So either it can be industrial drive or a grid application. Only the input side will change. Okay, so I just use the pointer. uh, I don't know how to get the pointer. Hopefully you can follow. Okay, so this is the input side. Okay, so basic of all this thing is that you require a inverter. So this inverter is shown here as a two-level inverter. Okay, so this two-level inverter has a very basic structure. So you have six switches. Every phase, that means actually coming output of every phase is basically each leg is contributed by each leg. So it has a top switch and bottom switch, and their respective gating signals is GA and GA dash. This complementary. You cannot sort them, so you cannot give a same output signal to this top and bottom switches. So it has to be complementary, and also there should be a dead time in between them, so that in order to avoid the sorting of the DC link. So this is the general structure, and what we are missing here. One thing we are missing here, that is between the output of the IGBT based inverters, and most of the industrial drives IGBTs are used for high power or medium power applications. So I am sticking to IGBT based solutions. And what is missing here between the terminal of the induction motors? Generally, induction motors, we need, that is not mandatory, but for a grid application, that is a mandatory something to put between the output of the inverter and the grid terminal. So that is actually the inductor. Okay, specifically a series inductor is required, or you can simple inductor, or instead of simple inductor you can put LCL filter also. The simple reason is that you cannot actually connect two voltage source. So when in terms of a induction machine, so it has a back EMF. That back EMF is represented by a voltage at this terminal of the stator, and then it has its own leakage inductance. So that leakage inductance can play a role, and actually that voltage difference between the back EMF and the inverter applied voltage, that falls across this leakage inductance. But for a grid application, you need to have a inductor, interfacing inductor, so that you can control the current by designing a proper leakage interfacing inductor for the grid application. So that is not shown here. So you have to understand that there's some sort of inductance is required, or in case of induction motors, it is obviously in terms of leakage inductance it is present. Or sometimes people put LCL filter for further filtering application. Maybe this is two-level inverter is not able to give proper quality output, so that need to be filtered. So that is required, that may require some LCL filter. Okay, so this is the basic structure of a current controller. Now we'll deal with different current control strategies, and different classifications of current controller. If we try to categorize them, so basically starting with VSI fed drive. Okay, it's not only drive; it can be grid connected system also. But I am writing in terms of drive here. So that can be of two types: either voltage control or current control. So voltage control here, USB space vector PWM control is very much popular nowadays. And current control is actually also a voltage source inverters, but in that voltage source inverter, your reference is current. That is what we saw in the last slide. So that current control can broadly classified into three areas. One is the hysteresis current control, then RAM comparison based current control, and predictive current control. So amongst these three, hysteresis, RAM based, and predictive current controllers, among hysteresis current controller is very popular because of its very fast acting operation and simple operation. Whereas ramp comparison based current control is regarded as linear control because it has some linear relationship of the current error it deals with and gives the output accordingly. So other, apart from ramp comparison based current control, other two control are nonlinear current control. But here, if you look at the hysteresis current control, which by inherently nonlinear in nature, it can also have two types. One is fixed tolerance band, another is a variable tolerance band. So fixed tolerance band is somewhat more easy to implement, and conventionally if not, some other problems are also associated to that, but conventionally it is used. Whereas you want to eliminate some of its disadvantage of the fixed tolerance band, you need to consider variable tolerance band, and in that also there are several different types are there: adaptive, sinusoidal hysteresis bands, phase vector based hysteresis boundary, and these are the different classification under variable tolerance band. Now, coming to predictive current controller will be discussing this thing in a very little bit of details. We will be discussing about predictive current controller. It is not always very convenient to use predictive current controller, but in some cases it is convenient to use. So we'll be discussing some of the features of each one of these. So but before coming to that, mean if you want to ask that why you would like to go for current control scheme, why not the voltage control scheme? So their basic answers are listed here. So then the first point, it says, talks about the accurate instantaneous current control, so and fast dynamic response. So that is the basic reason why current control is preferred over voltage control. Whereas both are actually using voltage source inverter, but the schemes of the control schemes are different. So current control scheme is always preferred over voltage control scheme, where you require a very fast dynamic response. Also, it has a inherent peak current limiting criteria. It can easily basically the point number 2 and point number 3 are interrelated. It has inherent short circuit protections. These two are interrelated. So as long as your current reference, what I mean by that, as long as your current reference is not disturbed, okay, so irrespective of some short circuit happens, so you are not actually shooting up the current, actual current, because actual current will try to follow the reference current. So you have to ensure the reference current is remain under control. So by that control methods, you can easily can maintain this peak current limitations and short circuit protections. And also very importantly, the last 2 points, it can have the effect, it can actually it is more it has the effect of load parameters, resistance and reactance changes, because any change in the load parameter, it is immune to those changes, it does not disturb by those changes, and it can easily be compensated. And also the semiconductor voltage drop and dead time of the inverter are also compensated inherently, and that is also a very important point here. So many works has been done in the literature how to compensate the dead time in a voltage source based converters, but here in current control, those dead time effects and voltage drop across the switches during the turn on condition automatically get compensated by the current controller. And of course that does not come free, so it has some well-known disadvantages like a large current ripple in steady state, generation of subharmonic component in the current, variation in switching frequency, that is also a big challenge in the current control strategy. So let us look at individually different current controls at a time. So first is RAM comparison based uh, RAM comparison current controller. So here actually, if you look at, I hope you are not This is not disturbing you. Let's put it at the last. Okay. So yeah, so RAM comparison based current controller, where there is a actually you need to use a carrier waveform. Okay, so here in the left hand side you can see easily you have a current reference. So for three phase individually you have three different current reference, I star, IB star, and IC star, and that is getting compared with your actual current, and the error, whatever the error is there, that is passed through by the PI controller to actually get a appropriate signal, which is to be compared with your current carrier waveform. Okay, and the carrier waveform is a triangular shape like this, and it has a certain frequency, the fixed frequency. And so but it has some disadvantage. This disadvantage is like there is a magnitude and phase error. So this has been observed in the right hand side. If you look at your current reference is depicted by a smooth line, whereas there's jittery lines, the waveform, jittery waveform is actually your actual current. Okay, so you can easily understand there is a offset between this reference current and the actual current, so it is not following exactly. And this was shown in this particular reference given by this paper. It's a very old paper, and it's a well-known problem of the RAM-based current controller techniques. This is a very well-known problem. So this you can easily observe, particularly when you have a low carrier frequency you are using for comparison. Okay, and so basically that result into a sinusoidal current error, and that also the offshoots, also the current ripples, which actually is more sometimes, and as well as it maintains a delay, fundamental delay with respect to the reference current. But this problem can be little bit minimized if the current if the triangle frequency is increased. Okay, this is a linear control. So but if you increase the triangle frequency, so you there will be lot of switching, and switching losses also at the same time will increase. So that is not a always very practical solution to do, but sometimes if you for some application this kind of RAM control is used, but this RAM control has its inherent problem as it is shown here. So we'll look at into other type of controller, and which is very popular in conventional hysteresis controller. This is obviously nonlinear control, or sometimes regarded as bang control or on off control. So here you use in the right hand side, if you see the control strategy, you have a current reference, and on both sides of that current reference you have a band, so plus and minus, okay, both side of the current reference, and your actual current is actually traversing through this band as you are switching on and off. The downside you have shown the signal switching on. When it's on, mean you are switching on the top switch, so it is getting some energy to current is rising, and when it is switching it off, so you are actually telling the current to fall, so it is falling in the bottom side, and when it touches the lower band, again you are switching the upper switch. And so this is also called a hysteresis, this particular window you are providing. So this is also a typical characteristics similar to the hysteresis band, so that's why it's called hysteresis controller. And here very importantly you are using three independent controllers. So independent controller means each of these phase has its own controller, so it is not dependent on the other phase controllers. So these are dependent controllers, but the problem is what is cited here, that it can result out a limit cycle oscillation. Okay, so suppose you are thinking of having a average switching frequency of 2.6 kilohertz as it's shown here, but sometimes in some places, okay, there are multiple of switching, as you can see in this particular figure. There are multiple switching, and those switchings is uncontrollably it is happening, and that is called limit cycle oscillation, and that may go up to 6.6 kilohertz as observed in this particular application. It is also referred in the same paper, is old paper, 1985 paper. And not only that, if you do this kind of application, induction motor or grid application, you also will may face this kind of problem. So when you are dealing with this conventional hysteresis current controller, and how much this band you will be want to keep, that depends upon you, but you won't be able to maintain the current error within this band, as the figure right hand side is shown very ideal figure, but actually your current will shoot up and go outside of this band at least 2 times of this band. It may go outside, so you are not very able to very closely follow the reference all the time. But there is no problem like my fundamental delay. That kind of problem will not be appeared here, but there will be some other problem like limit cycle oscillation. That means it will be increased frequency. As frequency is increasing, your switching loss due to high frequency, that will increase. Okay, switching loss will increase. So that is a concern. And also at the same time, sometimes your device what you are using, that may have some limit. Okay, that may not have the capability of switching at that very fast. So that is also a concern. So then people proposed the adaptive hysteresis band controller. Okay, so they thought that, well, fine, if we can control the band. Okay, the band need not to be a very constant band. So band mean the kind of band you are putting here, right? The shaded area. So both side of the reference plus and minus, it should not be equal. It can be variable. Why it need not to be equal all the time. So that concept came, and then people call it the adaptive hysteresis band. So adaptive, depending on the scenario and condition of the operating point, you are changing this band. That's why it's called adaptive hysteresis band controller. So they are trying to address the issues like the current ripple cannot be explicitly specified in the earlier case. So they are trying to contain the current ripple within some limit. Also, they are also trying to control the switching frequency variation. As we have seen earlier, wide change of switching frequency. So these two issues they are addressing in this adaptive hysteresis band. So there are a lot many papers in the history and literature. You search the papers in the Google or in the IITR Explorer, you will you will get all these different papers. But I am listing out these important ones, and I am also listing down some of the disadvantages alongside these papers. Okay, although they are trying to solve some of the issues, like in the first paper, there has a problem. There is a problem. Although they are trying to change the band, but they have a phase lock loop control based hysteresis current controller that might lose synchronization in the large tangent. So it might not work when some large tangent comes. That time it may fail. Whereas the second paper by Professor V.K. Bose, so they are also he is also trying to propose some control methods, current control methods using adaptive. But the problem is that it is a function of load and power and supply parameters. So you need to know the supply parameters as accurate as possible. So that knowledge is also required, and knowledge of the load is also required, so that you can optimize the PWM performance. So these are the limitations. Whereas in the third example, you can see they are also trying to do this in a unique manner, but actually that controller using a very complex feed forward term, and in any feed forward term if you use in the control, that may lead to some noise, or that may lead to some control issues, because if you don't put the right amount of feed forward term into the control feedback loop, so that might work in a very bad manner. Okay, if it is all right, that is fine, but if it is going to be a little different, so it may become worse. So that is another problem. So in the last paper is 97. So also it has also another issues, that although the efforts are made to control the switching frequency in a fundamental cycle, the variation of switching frequency over operating speed range is not examined. So they are actually neglecting the, although they are trying to do some improvement, but the switching frequency variation also not very carefully observed in that paper. So all of this paper, although they are trying to address some or other aspect, but they are not holistically a very good approach in overall sense. So either they are missing one or other feature. Okay, so people are basically struggling with these current control techniques, and all these current control techniques are talking about two level inverters. Okay, for two level inverters. So, so summary of the adaptive hysteresis band, that it is a little bit complex to implement because it has a lot of dependencies of load current and parameters, and it has stability problem, particularly during transients, and also it has limiting transient performance. So here is some example of this paper reference shown here, and that whenever you are giving a variable band, so you can see the current errors basically are not very fixed, so they are varying in the past figure, and correspondingly your frequency, average frequency, is almost constant. So in the first place they are using the variable band. In the second, the right hand side, if you maintain the band constant, so although your current errors are maintained in a specific bound, but your frequency, that is changing. Okay, dynamically that is changing over a fundamental cycle. So this kind of observation is shown by this reference. So but on top of all these things, that this has many problems as listed down here in these 3 points. These are the problems. So in a summary, we can say that though the better than previous two controllers, so basically previous two controllers mean the on-off control and the RAM based control. The predictive controllers are most complex and require knowledge of the load and extensive hardware, which may limit the dynamic response of the controller. So this is the basic limitation of the adaptive hysteresis band based control. Okay, now we are coming to model predictive control. Okay, so model predictive control is nowadays people are using a lot. If you will come across many papers, research papers are available. Okay, and why they have become so popular, there is a reason for that. So generally, if you want to work with the previous controllers before this model predictive controllers, okay, these three type of controllers, okay, if we find out here, these three controllers, right? So they have a problem, right? They have a problem because they cannot work apart from their inherent problem. They cannot work with multi-level inverters. Nowadays, multi-level inverters are coming. Okay, so when the multi-level inverters are coming, there are many number of levels, voltage levels at the output, more than two, and it is not a very simple then to control the current. I mean, like on two level, you have either you switch on the top switch, so current will rise upward, and if you switch on the bottom switch, current will fall downward. And in multi-level inverter, there are many states. For example, three-level inverter, it has a zero state in between, plus and minus in between, there is zero state. So how current will behave during that zero state, so this is little different than the two-level inverter. So probably you need to use a multi-band instead of a single band, okay, or multi-layered band. And these thing will become more complex as the number of levels will increase. It may, in a five-level inverters, it may increase, complexity will increase immensely. So and on top of that, there will be stability issues and all during transient conditions. So, in order to avoid those issues, the model predictive controller, basically we call model predictive controller, but basically it is a current control technique, correct? So here you are making use of a model. You are taking the help of a model which is known to you, and that model is basically nothing but some equation that is coming from the knowledge of your plant. So if you know the plant, and if you give some response, what should be the output? You give some input and what should be the output, if you know, and if you can model using some mathematical equations, using some electrical parameters, and those electrical parameters you know, then you can easily model it. And in advance if you give some input and what should be the output. So that's what it's called model predictive. So you can predict in advance. So if you give some input at the kth instant, what will be the output at the k plus 1 instant? Okay, so if you know the equations, you can easily find out in discrete manner. So, so the positive note of this model predictive controller is that it requires high calculation power, and that was earlier limited by some calculation limitation of earlier limited by the some microcontroller limitations. But now in present days, the standard DSP, digital signal processors and microcontrollers or FPGAs are coming. They are quite fast enough. They can easily take care of this little bit of time consuming process which is involved in the model predictive controller. Sometimes the basic multiple controller searching has a searching algorithm. It searches the basically it has a cost function, and the cost function, in order to minimize that cost function, it searches many possibilities in the inverter states, so, and to find out the best the lowest cost function, so that your current is being tracked properly. Not only that, it can also meet out other objectives. So, so that kind of calculations require some uh, exhaustive calculation. Not very complex though, but it requires a many number of calculation. But in modern DSPs and microcontrollers, that can be easily done. So that limitation is overcome present day. So model predictive controllers becoming very popular. And all, not only that, it can also take care of many objectives. Okay, yeah, so interesting applications can be found in those topologies where modulation techniques are complex, such as for matrix converters. Yes, so in matrix converters or any higher level multi-level converters, and modern modular multi-level converters are coming. So they have many objectives to fulfill. Not only the output voltage, you have to maintain the input current quality, you have to maintain the voltage balancing capability of the capacitors which are in the circuits. So they have many objectives to be fulfilled. So where there are many objectives to be fulfilled, so that modulation techniques become complex, and in those scenarios you can find out a objective function which is which comprising of many inputs. Okay, many, so that will take care of many objectives. So that will take care of your that multi-purpose role it will play. So that way it can play a very simple way to approach your and to find out the best possible input. What is the input you should give in order to track a particular current at the output. At the same time, you can meet out the other objectives, internal parameters also you can maintain. So one of the reference is shown here, a model predictive control, simple and powerful method to control power converters. Okay, you can easily go through this reference. I will share these slides so that you can get all this information. You have to note it down here. Okay, but this anything in this world does not come very freely. That comes with some drawbacks or some cost. Okay, so some criticism also is there from the application engineers about the model predictive controller or MPC. So they say sometimes this controller appears to be complete, so optimally in both economic and regulatory control, ability to handle plan inputs and outputs, and a centralized structure for coordination. That means that is what I said. But there is no guarantee that mathematical optimization of MPC translate well into engineering objectives. So there is no guarantee. Why there is no guarantee? Because you need to be dependent on many parameters. Because when you have a model, you need to know the parameters as well. So when the parameters are unknown or it is not known accurately, then there you probably fail. Okay, there this model predictive controller might not work nicely. And also this third point also talks about that thing, parameter mismatch may lead to non-functionality. So if you know this plan very well in advance, then this might work nicely. Otherwise, also it may not work. So apart from all these things, it cannot also control the variation of switching frequency very nicely. That is also another disadvantage. okay, so of model predictive control. So that is not written here, but that is also another disadvantage. So variation of switching frequency also a concern in model predictive current controller. Okay, but some of the cases it might work much better way than the previous few type of current controllers, and it also works nicely with any multi-level converter topologies where very complex PWM techniques are involved. It works nicely. Okay, but it has also has some disadvantages. So now, so there are another techniques proposed recently from 2013-14 onwards. So this kind of papers are, or before 2011 onwards, I would say, this kind of papers are available. So this is called space vector based variable band for induction motor drive application, where this is completely different approach than the other previous three current control approaches. So here, but it is a part of that band kind of concept, but this band is not individual to any phase. So here we are trying to combine all these three phase. When we are trying to combine all these three phase, and we call it's a space vector or space phasor. So instead of looking at individual phase current error, we are trying to look at the current error in a plane, alpha beta plane. Okay, that is called space phasor plane. So that in that plane, the current error delta I is the difference between the actual current and reference current. So now, if you try to solve those current error issues that has been already reported in some of the papers. So their very uniqueness of this paper is that it can able to maintain the switching frequency, which is none of the previous current controller was very emphatically was able to control. Okay, although they are trying to control in some way or other, but they has their own limitations. But here, ideally, you can do that control, the switching frequency variation control. You can do nicely by doing some nearly constant switching frequency control approach. Okay, like SV PWM kind of approach you can use in the current control itself. So the SVPWM approach is for voltage control, but similar control approach can be also implemented in current control. So here some of the examples are shown how initially the study was seen that how the current trajectories are actually look like in a SVPWM. Similar to that, a current boundary is set up. Okay, so when actually you are moving from some one portion to the another portion of the sector one, okay, from 0 degree to 60 degree of the space phasor diagram. So then you will get this kind of current error trajectories, and accordingly you set up some boundary. You give a boundary, and then once you give the boundary, then your current controller will work based on this boundary. If you're trying to going outside of this boundary, you switch appropriate voltage vector so that current error remains within this boundary. So using that technique is called space vector based variable band induction variable band current control technique. Some of the results are also demonstrated here. See, look at this. This is a 5-level inverter, right? So I was earlier talking about that other controllers were not very good at multi-level inverters, but here this controller is good at multi-level at any point, any multi-level inverters. Here, this is the example shown for 5-level inverters hardware results at 10 Hz operation, where you are changing the reference quickly and it is quickly tracking that reference without any loss of stability. Okay, so it is inherently very stable, and that is also one of the, it is basically one of my work in 2013. So that is for 5-level, you can see here. So this is also called as nearly constant switching frequency, because if you look at the spectrum, if you compare the spectrum with the SVPWM, which is the voltage control, and the proposed current control technique, so at 10 Hz and 20 Hz, this look like SVPWM spectrum. So that way it can be concluded that this particular control is able to maintain a particular switching frequency, although it is not very fixed, but it is quite tight. It is very tightly controlled around its design switching frequency. And the zoom version of that also will be, you can see here, you can easily understand. So apart from all these advantage, there are another advantage is that the optimal voltage vector switching. So the way voltage vectors are switched, basically when you actually designate the voltage vectors, you are you give some name, right? The v1, v2, v7 and v8, the conventional name is given in any space vector strategy. So that way, if you look at the sequence of vector application in a current control, so that sequence is almost similar to the sequence of a voltage controlled SVPW. Okay, so that actually depicts that, that says that you are able to control, you are able to switch the voltage vectors, okay, very optimally. Okay, so your current errors in the D and Q axis are not very spreaded, right? It will be controlled, and it will be done in a very controlled manner. Okay, so these are the few features, good features are available using this strategy. Okay, now next, okay, that's all about the current control techniques, and hope you have got some idea and some indication that what are the current control techniques available in the literature, and how they can be categorized, and some of the references, well-known references, you can also get to know from this discussion. Okay, till now. So if you have any queries, you can stop me here, or I can address them at a later section. Okay, so next point, I'm coming to a different topic. Okay, so this topic is about the SGPWM, SPWM, and thereby I'll be going next to how I am able to get a better receivers utilization of any two-level inverter. So I'm discussing here for two-level inverter. Similarly, it can be extended to any multi-level inverter. So that's not a problem. So things will remain the same. But the basic fundamental idea, which you can derive from the two-level inverter, that can be easily extended to any multi-level inverter. So here, that's why I am showing the two-level inverter circuit. And here you have the input Vd, and you can assume a capacitor. Generally, input side you have a capacitor, and the midpoint of, if you assume the two equal capacitance are available, C and C, and midpoint of that is the 0 point. They are connected in series. So with respect to that 0 point, okay, so you are actually modulating the output of every point. This point is called pole voltage of A phase, and so this point is called pole voltage of B phase, and this point is pole voltage of C phase. Whereas if you look at the voltage from this point, from the load side, if you look at, so from A with respect to N, that becomes a phase voltage. Okay, so generally we talk about pole voltage and phase voltage. These are the two different quantities. They are not same. As long as this point, N point, is not connected to this O, when they are not connected, that means they are disconnected. So then they need not to be the same voltage. Okay. So here I'm coming to this first of all, the SPWM technique, sinusoidal pulse width modulation technique, where you use a sinusoidal. So forget about other two waveform. First, let us concentrate on the sinusoidal waveform. So here in the one side, you can see the positive side. This particular sinusoidal waveform goes outside of this particular horizontal line. Okay, and this horizontal line is nothing but your limit of your carriers, right? So basically your carrier, this is used for control purpose, not the output voltage. This is the control inputs signal. Okay, these are the control signals, and these control signals to be compared with these carriers. When you trying to compare these carriers and get the pulse, we are generating the pulse basically out of this comparison. And then you see here when it goes outside this line, maximum line, okay, or you can depict as +1. So then you are actually reaching to the overmodulation, okay, and you don't want to reach actually overmodulation. If you want to reach overmodulation, what will happen? So you will unnecessarily introduce some of the lower order harmonics. Okay, so the basic fundamental idea of using PWM operation of any inverter is that you use a sufficiently high frequency carrier waveforms to compare, and these carrier waveforms will determine what should be your switching frequency of the inverter, and that will be output nature, what will be the harmonics, dominant harmonics will be there, that will be determined by these carrier switching carrier frequencies. Generally they are at least few in normal conditions 21 times more than this frequency are 21 times more than the fundamental frequencies. Then you need not to worry about synchronization and all. So if you can assume that kind of ratio, the frequency ratio of carrier frequency and the fundamental reference, the carrier frequency are 21 times, at least 21 times faster than the fundamental. So that way, if you can think of, then your rest of the analysis of your rest part of the analysis will be much easier. So now what I was talking about, that this overmodulation, when you are doing this overmodulation, then you are introducing some low order harmonics which are lower than this particular frequency of the carrier, and not so those are very difficult to eliminate. Suppose these are the load, this rectangle blocks are shown, these are depicted as a load, but in between these points you need to have a filter, right? This filter is not shown here. So this filter need to eliminate some of the harmonics or some of the unnecessary component apart from the fundamental components, right? You need to eliminate those. So if there are low order harmonics, then they are very difficult to eliminate, because your design of your filter basically done by L and C value. Okay, if it is LC filter, so the requirement of C and L values will be quite big. So we don't want to increase the size of the L and C, and not just for the volume purpose, but also from the loss purpose also. If you increase the L size, it will give you more loss. Okay, some resistance will be there, it will give you more conduction loss. So you need to keep these filters as small as possible. So you need to so don't want to involve, you don't want to get into the overmodulation. So you want to retain everything, all the signal within this particular line. So how you can do that? That you can do using some third harmonic signals, third harmonic with respect to the fundamental, right, which you have already considered. And it should be like this, okay, so that this particular, if you add these two original signal and this third harmonic, your resultant waveform will be like this in wavy in nature, and that will pull down this peak of the previous original peak, will get pulled down to the lower value, and these heights will never, the two maximum heights you are getting, that will never cross this particular line. So you never entering into the overmodulation. So that way you can inject a particular amount of particular amplitude third harmonic signal, so that you have all your signal for comparison purpose, all three phase signal is coming under coming within the linear modulation zone. Okay, you are not going to non-linear over modulation zone. So basically when, and then this third harmonic, you are not worried about this third harmonic in the phase voltage, because either line to line voltage or phase voltage, if you look at this third harmonic gets automatically eliminated. Okay, third harmonic automatically get eliminated, so you are not bothered about to inject any third harmonic appropriately. Okay, now so that way basically you can get extra margin, okay, extra margin or extra fundamental waveform at the phase voltage, okay, or at the line to line voltage, okay, not in the pole voltage, but pole voltage will be like this, but your fundamental or line to line voltage will be purely sinusoidal, because there no third harmonic will be present. Okay, so this way you can inject some amount of third harmonic, but still you will not be entering into the overmodulation zone. So that is basically called DC link utilization, enhancement of DC link utilization. So you are not increasing the VD value or VDC value, still you are able to get a sufficient amount of magnitude. Okay, you extract maximum amount of magnitude in the phase voltage. So okay, so if you just, you can always compare this SPWM technique or sinusoidal triangular comparison method with space vector methods. Okay, it is called SPWM technique. So there is always the equivalence between these two. I will talking about this equivalence in the next slide. So these are not very different from each other. So if you look at from the space vector technique, what you do, so you basically, in order to get a particular reference VR, what you do is basically you switch V1, V2, V0 and V7 in a switching cycle, right? So basically you are doing a volt second balance operation here. So that way you are getting a resultant in a TS cycle, the volt second averaging technique, you will get a resultant vector here by applying V1, V2 and V0 and V7. Okay, these are the vector locations, and this tip of the vector equivalent vector is VR. You can get by averaging these four vectors or three vector locations. Okay, so but these are nothing different, they have equivalence. How they are equivalent, I can briefly tell you. So basically, before going to that, you have to understand what is the moving average by volt second balance. Just now I was talking, in case of in space vector PWM, there is a comparison of carrier, right? When you have a comparison of carrier, I think I can write here, yeah. So this is a carrier, right? So this carrier height is actually 2 VC. Okay, this carrier height is 2 VC. So then whenever there is a crossover, okay, the crossover time, you can easily find out. From the starting point is here, from here to here, you can easily find out the crossover time. So so that time you can easily find out by this equation, right? So this is just it will be if here actually TS and TC are same. In this particular picture, if you look at the pulse, actually PA0 is a pole voltage, VV0 VA0 is a pole voltage of A phase, VV0 is pole voltage of B, and correspondingly VC0 is pole voltage of C. So here the first cross is the C. Okay, it is crossing. Okay, B and A is little the upside. So first it is crossing the carrier because it is the lowest value. Okay, so as it is a lower, it is crossing this particular carrier the fast. So here this particular time you can easily find out by this mathematical calculation, right? So if you find out this is the entire TC or TS, okay, TC is equal to TS here, this entire TS or TC, then you can find out the S1 on, how much time S1 is on, okay, by finding out this timing, okay, this duration of time. Okay, this particular duration of time you can easily find out. So that is the expression of that. And S2 actually is the bottom switch, S1 is the top switch. So initially it was on and then it is going off, right? So S2 is the bottom switch. So bottom switch will be the difference between the time of the total time minus the time when S1 is on, the top switch is on. The rest of the time S2 will be on, right? Bottom switch will be on because they are switching in complementary manner. They are switching in complementary manner, so rest of the time S2 will be on. Obviously, you are not considering the dead time. Dead time is neglected. Now, so if this is the time, so you can easily find out that this time into this voltage plus this time into this voltage divided by the total time, that will give you the average voltage. So average voltage is always maintaining a proportionality with respect to your Vm. Okay, so this is the Vm, the sample value, right? Where you are crossing, this is the Vm. So this is the Vm. Actually, the length of this is Vm. Okay, so based on that, always maintaining a proportionality with respect to your VDC by 2. Okay, and the carrier, and the given for a given carrier VC value, this is always maintaining a proportional relationship. Okay, so as long as this relationship or this volt second balancing is maintained, so you can easily find out that now this part you have understood, the right hand side, this is for a particular sample. Now if you look at the waveform, complete waveform, so in this complete waveform, if you look at, you'll see they have at different places. So in a particular place you have seen this right hand side, but this scenario will change depending on the location of the sample. Okay, so here in sample 1 you are taking one sample at sample 1, and there in between several samples are there. Several samples means several TS intervals. TS, there will be many TS intervals in between. So like that, you can have sample 2, you will get different scenario, which is different from sample 1. So as you can see, if you look at this entire waveform, so they are not very equally spaced. The envelope, if you look at the envelope, you cannot cross this +1 and -1 boundary. Okay, if you cross this boundary, you are actually entering into overmodulation. So you are not supposed to do that. So, but you have a different gap, right? You have a different gap. So when it's a particular, in this case sample 2, if you look at, so the gap, the maximum value is VB, and the difference between VB and the 1 is this much, whereas the difference between this VC and this -1 is this much. So they have a different values. When they have a different values, so there is a chance that you may hit the limit very quickly. Okay, so once you can hit the limit, you cannot further proceed. So if you are increasing the modulation index further, so the peak of this waveform will increase further. So you will quickly hit the limit, and further you cannot increase the amplitude. So with sinusoidal waveform, you will hit the limit quickly. Okay, so but if you add some offset, okay, if you add some offset in this sinusoidal waveform, or you add some third harmonic waveform, okay, both are the meaning are the same. Either you add this third harmonic or you add some offset, so this actually envelope will become symmetrical. Symmetrical in the sense they are equally spaced between this +1 and -1, and that is what, when they are equally spaced, that is what we call SVPWM. So that is exactly SVPWM is doing. So SVPWM, when they're equally spaced, so your zero switching timings will be same. When they're equally spaced between +1 and -1 boundary, that means that topmost envelope and bottommost envelope will be equally distant. In any particular sample, they will be equal distance from the top side and the bottom side. That means your timing from the zeros will remain the same, and that is what we do in conventional SVPWM technique, space vector technique. You always try to keep the zero sequence voltages, sorry, timings. Okay, the zero timings here and here, they are same. Okay, here you can see in this particular example, T0, T0 by 4 and T0 by 4, they are exactly same, and here this T0 by 4 and this T0 by 4 also exactly same. So that is the only thing that makes the difference, okay, between the SPWM and SVPWM. When SPWM, you add the third harmonic, appropriate third harmonic, then it becomes SVPWM. Okay, automatically it will become SVPWM. Or if you switch them in such a way, these two intervals are same, the starting of the zero sequence and end of the TS by 2, end of the TS by 2 time, the zero voltage duration are same, the both side, then that is also become SVPWM. So the meaning, both the meanings are the same. So if you can easily understand the limitation of SVPWM by this circle radius. So this is limited by 0.5 Vd, whereas the SVPWM is limited. It is actually, it has a larger radii compared to your SPWM. So maximum length from here to here, from here, here, sorry, from here to here, you can assume 2 by 3 Vd, okay, this length, okay, and if this length is 2 by 3 Vd, and then this length will be what? 0.866 into 2 by 3 Vd, okay. By the geometry formula, you can find out easily. So this will become something approximately 577, something like that, Vd, correct? So this 0.577 is obviously more than your 0.5. So this much extra you are getting, and this extra is 15%. This extra is 15%. So even third harmonic injection also will give you the same in increment, but you have to appropriately use the appropriate magnitude of the third harmonic. You have to implement. So that appropriate magnitude is that 1/6. The last but one point is written 1/6 magnitude of the fundamental component. So if you implement that, then that will give you the same increase in the fundamental voltage, the 15.5% increment. So this is also possible same way using SVPWM technique. But sometimes to actually create a third harmonic waveform is difficult in practically, right? So once you give for a given signal, how to you have to lock that third harmonic signal with the fundamental signal, and that fundamental signal also can vary. Frequency may vary, its magnitude can vary. Accordingly, we have to change the third harmonic magnitude and frequency. So that is a little cumbersome technique if you want to really do using this third harmonic injection technique. But rather, SVPWM technique is much easier, because by controlling the duration of the zero vector, you can easily do using a digital controller. Okay, but the effects are the same. Okay, but the effects are the same. And okay, first let us go by one. So first point is, you have understood the maximum inverter line voltage can be boosted by 15.5% by third harmonic injection methods. It is done by adding a third harmonic component. Okay, and the injected third harmonic component will not increase the harmonic distortion. That is what we that is actually low order harmonics will not come. It will not enter into the over-modulation zone, and the line to line voltage is given by this, where the third order harmonics are the same magnitude and phase displacement and thus cancel each other. The optimal injection level, that is what we have said, 1/6. And it's also observed that when you will get the best possible TSD, that is not 1/6, that will be 1/4. That is observed actually, that if you want to get the best TSD compared to your sinusoidal PWM, obviously TSD can be improved, and that best case will happen when you have 1/4 of the fundamental the third harmonic magnitude will be 1/4 of the fundamental. Okay, these are the few observations, but as I said, that SVPWM is through the digital control is much easier. So apart from doing this thing using third harmonic injection, it is always better to control the duty cycle of the zero sequence. Both meaning are the same. Here I have explained the meaning are the same, and you can easily control by digital controller. Okay. Okay, so all right. Probably I'll give a stop here, and probably I'll see some of your queries if you have. Hello, do you have any queries? Then I can take it up. Do you have any queries? Hello. So shall we proceed? Can you just respond me? Otherwise, I can proceed. If you respond me to continue, I'll continue. Hello, can anyone write me in the chat box? I'll also take a small break, drink some water. Okay, so let me share my slide again. You can see, I think. Okay. If you cannot see, just let me know by pinging me. All right. Um, So till now we have understood the DCLink, how we can increase the DCLink bus DCLink enhancement. It can be done using some small technique in the PWM, some either through SPWM third harmonic addition approach, or you can digitally you can add some offset so that your distribution of the timings can be rearranged, and it can be equal in the both side first and last switching, or this the zero vector switching timings can be made equal. Okay, so now let us come to the basics of multi-level inverters. Okay, so this much talked about in recent times. A lot of research is going on in this particular topic and different aspect of it, how to improve the efficiency, how to improve the different control functionalities, how to make it more optimized so that you can get best out of it. So a lot of different aspect of it. So it is being used by the industries also. It is not that it is simply academic interest. It is also being widely used in the industry. At least the 3-level inverters up to 5-level inverters are a successful products of many MNCs nowadays. And this particular picture I have showing here, probably this is the taken from Venus reference, but I think it's the product of ABB. So they have the 3-level NPC inverters. Okay, the neutral point clamp inverter FET MV medium voltage drive. So these multi-level inverters are mostly used for medium voltage drive, not for low voltage drive, because in low voltage you don't require you have so many switches are available to block the required voltage in the receiving voltages. But where you if you increase the magnitude of the voltage, so a particular switch cannot or available switch in the market may not be able to block that voltage, or at that particular DC link voltage it cannot operate. So you need to if you don't use MLI, so you have to use those switches in series, okay, to block that particular voltage. I'm not talking about the high current application. I'm talking about the medium voltage or probably high voltage application, where you need to use many switches in series connection in order to get the total voltage blocking capability. But the problem comes with if you add many switches in series, so there are many problems that they have some difference in the voltage blocking. So either you have to do a static balancing or dynamic balancing technique you have to apply, or apart from that there will be some other issues of switching timings. you cannot make them all switches on at the same time. Okay, so there may be some delays in synchronization issues. So that might cause some switches to fail for the transient operation cases, or some of the over voltage may appear across some switches in the series connection. So in order to avoid those pitfalls, there are several multi-level structures that has come. So popularly, three-level many structures are available. So I'll be talking about few of the three-level configurations here. But before that, some of the basic features as depicted by many authors, are particularly, and the leading authors in this, contributors in this particular domain is Rodriguez. So from there, if I quote, so they have a reduced dv by dt, because dv by dt contribute to lower dv by dt contribute to lower switching losses as well. So low common mode voltage as well. So sometimes some applications common mode voltage play a devastating role, particularly drives application. Also some of the pv applications, they spoil the circuit or the particular device over a long period of time. So the common mode voltage also can be eliminated. Some of the MLI, or can be reduced in some of the topologies of the MLIs. And output voltage.
Sir, change your to slide mode presentation.
Okay.
Okay.
Yes. Now it is fine, I think, ma'am.
Yeah.
Yeah. Thank you, ma'am. Thank you. Yes. So now it is visible clearly. Now output voltage with less harmonic distortion. So that is the implication of this particular point, is that you need not to use a very high filter, high volume and high weight of the filter, right? You can use a small size filters. Okay. And then a high efficiency, the why high efficiency? Because if you are able to reduce the switching frequency of a particular switch. So if we compare a switching frequency of the inverter, that might be the same at the output level, but if you look at the particular switch, individual switch, that may be switching at very lower switching frequency. So that way you have high switching frequency overall. Okay, high efficiency overall. So that way there are several advantage. And MLIs can be single source based or multi source based. So classical MLIs are diode clamp MLIs, that is neutral NPC, we call neutral point clamp NPCs in general. There are flying capacitors MLIs, the cascaded edge bridge MLIs, and of course the combination of all these three, that comes under the hybrid topologies, and that are also there. And single source MLIs make use of capacitors for multiple voltage level generation. So there are some issues with capacitor voltage balancing in the DC side also, that I'll be discussing in tomorrow's class, but not today. And then capacitor voltage balancing scheme, not only for the DC side, but also in your main circuit towards the load side also, they can be sitting there as a flying capacitor. They need to maintain their respective voltage. So that is also a challenge sometime for multi-level inverters. But actually, if you look at the basic thrust area, why these multi-level inverters got so much of prominence in present days, that is because the availability of the low on-state voltage strange gate IGBTs. The strange gate IGBT is a particular technology, manufacturing technology. So that will give rise to very efficient IGBT switches that have lower conduction loss and lower switching losses. And of course, they are not failing to, they are not prone to any failure. Okay, IGBT failures, that like earlier IGBTs. So they are very reliable. So since this technology has come, the MLIs has become very popular in the market. So what is basically MLI in a very conceptually, if you look at? So if you have a pole voltage, okay, this pole voltage two level, first you look at the two level. So as I said earlier, you can assume it actually two capacitor, and the midpoint of this two series capacitor in the input DC link is can be treated as a reference point, and this is N. So with respect to N, if you look at the pole voltage as when it is connected to the top one, and that is the top switch is on, and it can be connected to the bottom one when it is connected to the bottom terminal. Okay, so depending on that connection, either it can get plus VDC, and or it can get minus VDC. So it has a two combination, two possible output voltage levels. That's why it's called two level. As you can see here, for actually realizing a sinusoidal voltage, fundamentally you need to have to switch randomly, but the switching levels are actually between either plus VDC or minus VDC. These two levels are only available, so we have to synthesize these particular fundamental out of these two levels on. But whereas if you come to three level, then you have many more, you got little more flexibility, because and your jumps around the voltage levels are less. That the changes level voltage changes from here you can do. You also have zero level of the voltage, so you can change jump between zero and plus VDC, and in other the other half you can jump between zero to minus VDC. So obviously you have less dV by dt, as I said earlier, and there are different. They have a different implication in terms of common mode voltage, better common mode voltage also. Okay, so those will be different chapter altogether, but as conceptually you can see that you can get more number of levels, not only three. Suppose the variable is m, so but you need to have different tapping points. So if it is a m level, so you need to have a m tapping points, whereas the a point is fixed here. So the a point is called pole. So pole is fixed to a load, and most of the loads are actually your RL type of loads, right? So you are not supposed to change the pole, right? When any any connects AL or inductance is connected to a particular point, that point is called pole. So you are not supposed to change. Either it has to connect to either of these terminals. So you always provide the path for the current to flow. Okay, that's why it's called pole. But if you look at the waveform, you have a steer like waveform, right? When it's the m levels, m is quite big here, larger than 3, so you have many stairs, okay, in the terminal, in the output voltage. So it is very easy to synthesize the fundamental output with less number of harmonics involved. So, but this is about the synthesis and the amount of harmonic PhD contained in the output voltage. But what about the losses? If you look at the losses, that is shown in the right hand side. So if you just compare between two level and three levels, the data is I have got. So you simply look at these are Mitsubishi switches used. Okay, and the particular application is grid application, grid operation of converters, which is at a 750 volt the grid voltage, which at frequency of 8 kilohertz and a modulation index of 0.85 and the displacement power factor of 0.98. So if you compare the same situation for two level and three level, and as you change the current here, okay, and this is shown as a normalized, so that's what in ratio it's shown. But if you change the current, output current, and you can see that there is a change in the loss. Okay, the loss incurred due to conduction loss and due to switching loss. But if you look at the two level operation and three level operation, the difference in the losses. Okay, so either in the rectifier mode or inverter mode, does not matter. All any one of these modes, three level converter losses is little bit lower than or considerably lower, I would say here, lower than the two level converter, because this converter is supposed to run at 24/7, so all the time it is connected to the grid. So that small amount or whatever power saving you are doing, that matters a lot. So this much saving you are able to get in 3-level converter, adding this loss actually both conduction loss and the switching loss using Mitsubishi switches. Okay, these are the case study. So you should feel actually encouraged by this data that any multi-level is not only have some other advantage, but also it has some efficiency improvement. Although you have to pay for some extra extra investment in terms of more number of switches. Okay, a little bit more big in size and weight, but they have some other advantages. So basically, if we try to classify multi-level, so as we know, there are three different types: neutral point, cascaded, and flying capacitor. I will not be talking about cascaded edge bridge today because cascaded edge bridge by nature, because I thought of explaining three levels, so I'll be sticking to NPC and FC, but cascaded I'll be take up in the tomorrow's class. So let us take one by one examples of NPC inverters. First is it's also called diode clamped MLI. Okay, so why it is called diode clamped? So all of you know, you probably familiar with the structure. Those who are into in this field, little bit higher studies, they have done their higher studies in power electronics. So they are already aware of these structures. So diodes are actually getting clamped through this diode. The pole voltage getting clamped to the neutral point voltage. That's why it's called diode clamped. And there are three different switching switching states are possible for getting the three different voltage level at the output, and this is shown nicely here in the corresponding voltage output level, corresponding voltage switches need to be turned on. So this particular plus VDC, you need to turn on both S1 and S2 here. And for the middle voltage level, zero voltage level, so you need to turn on both S2 and S3, and then for the bottom one, you have to turn on both S3 and S4. Okay, so basically these are bidirectional switches. So depends. It does not depend on the direction of the current. Okay, so any direction of the current path will be provided either through the switch or through the anti-parallel diodes, which is inherent in the IGBT switches. Okay. Okay, so these are the conventional technique, but yes, of course, the problem comes with the balancing of these capacitors. There are a lot of work has been done, a lot of attention has been given in the literature, because these are the real issues when you go to the field, because ideally these capacitors may not diverge from each other. They will remain VDC and VDC, assuming the total voltage at the input side is 2 VDC. So they will share the equal voltage ideally. And also, if you try to simulate in your MATLAB or Plex or any software, so you also be seeing that these voltages are almost more or less stable. The reason behind this is that you are assuming that everything is ideal, everything is symmetrically, all the switches are symmetrical characteristics. So that's why this you will not face this kind of problem. But as you go on hardware, run any hardware setup, you will easily observe these voltage are diverging from each other and probably settling to say a particular value which are different from each other. Some maybe this may be more than VDC, this will be less than VDC, but total voltage will remain at 2 VDC. So but then your output shape will change. Output shape will change. So that's the problem. So you need to maintain this voltage respectively at their VDCs. So that issues we will be discussing later, not today. Okay. So so neutral point clamp inverter. So if you try to summarize, so it has a multiple voltage levels through connection of phases through a series bank of capacitors. Okay, this is a capacitors bank. The diodes clamp the switch voltage to half the level, as I said earlier. So the advantage is that it is very popular topology. Basically, Akagis they have proposed this topology in way back 1980s. Okay, it has a low device count, good harmonic profiles, suitable for medium voltage applications, but there are some drawbacks. And if you go to the implementation level, it increases the number of clamping diodes. Okay, because the clamping diodes are the main source of the losses actually, because of reverse recovery losses and other losses. The issues of unequal power loss, obviously the power this heat dissipated across the switch S1 and heat dissipated across the switch S2, they won't be the same. And also the complexity in the DC link capacitor voltage balancing control, that is always there. Okay, so sometimes these are the issues challenged by the engineer, challenged by the engineer. So some of the studies are also provided. Those studies you can find in this particular reference is provided in the bottom. Okay, okay, so that is they are studying basically the 2-level and 3-level converters again, and in order to find out the efficacy of these 3-level inverters. Here again you can one small observation from these lost characteristics. You can see when you compare this 2-level and 3-level using some different similar actually switches, IGBT switches. One is that this punch through technology and non-punch punch through technologies they are using. So both are having almost similar characteristics. So over a particular frequency, switching frequency, basically you are changing the switching frequency here. Your 3-level is actually giving better efficiency than your 2-level. So if you are actually really thinking of you have the option of using 2-level, so if it is a low frequency operation, probably it is better to stick with 2-level. But where you have option of either to use 2 or 3-level, better to go 3-level when your switching frequency is in the higher side. Okay, so this is the particular observation and also shown in this particular reference. And if you try to have a cost comparison analysis, so this is very interesting observation. And also same paper, same reference it is given. I'm taken this from the same reference. It is very interesting observation. If you are worried about the loss, if you are a businessman, so you would invest your every penny with proper justification. So you need to really be concerned about the money you are putting in for investment, right? So for this particular frequency operation, 4 kilohertz, if you compare 3-level converter and 2-level converter, the inductor is not only about the switches and the inverter structure, but the associated so many other things are involved, like the inductors that is required for filters, and AC filter capacitor that is also involved. But if you compare, there is a difference. Okay, there is a difference. Particularly, the difference is more when this FS is 8 kilohertz. You are going the little higher side. Okay, look at the inductors, money involved in inductors. There is a lot of difference between 150 3-level inductor size got reduced. You are saving the money for the inductors. Okay, and particularly the IGBT, you see, if you go, that is very surprising. So IGBT also you are actually getting lower values of lower price, although your number of switches got increased compared to 2-level, because your rating of the voltage also reduced, although your number of switches got increased, but your rating of the voltage and got reduced, so your price also got reduced. So you don't require fast diodes in 2-level, but here you require fast diodes, so you have to pay for that, but you get improvement in all other aspect in terms of cost. Like common mode filter, also you require lower common mode filters because it generates lower common mode voltages. Okay, and but if you look at the control hardware, which is the control platform, will remain the same. Sensor wise almost remain the same, and heat sink wise little less because it gives you lower losses. So this heat sink also will be little lower side. And gate driver, it has to increase because it has many number of switches. Okay, so that way if you compare overall, you get much better price uh, compared to a 2-level converter when your switching frequency is increased. So apart from this NPC, there are another structure is called NPC. and that is derived from the NPC structure. But actually, the NPC has the problem. The diode clamp based NPCs has the problem. So that diodes are actually replaced by active switches. That's why it's called active NPC. Okay, so it's called ANPC inverters. So that is that. I'm not spending much time on this, but the advantage of this is that it distributes the power loss uniformly and control the junction temperature. It improves the cooling system design and increases the output power ratio. So these are the reference. All these points you'll get in this reference, but it comes with one drawback, that increased number of switching devices. Obviously, when you are replacing these diodes using the IGBT switch, so you need to control this switch. So for that you require a driving signal. For that, gate driver circuit are extra, so you have to pay for that. Okay, so all these observations are you can see in this particular reference, but it has some advantages in some particular applications. Okay, so when you actually going for a little higher power application, so this ANPC can behave better than your NPC structure. So another very important structure in 3-level category is that T-type converter topology. So so basically these are little different from in the sense, because here again you are using total 4 number of switches per phase. Okay, but the rating of the switch here is T1 and T2. They are two different ratings. Okay, so T1 are actually higher rating switch, and T2 and T3 are of the half rated switch. Okay, and if T1 is 1200 volt switch, you are the standard switch available, you can use. So T2 and T3 will be of 600 volt. Okay, and you can, for example, you can use a opinion this but switch for the top and bottom switch. Okay, for this leg, and when you are trying to clamp this neutral point, and that clamp will be clamped through this particular two switches, anti-parallel, it's called bidirectional switches. Okay, it's called bidirectional switches. So the two switches, but they will be of half of the rating of these two top and bottom switches. Okay, so again, if you compare this T-type inverter, they have actually again, if you compare with the variable switching frequency, when you're changing the switching frequency, again you will get the advantage, yeah, advantage in terms of switching losses. Okay, so you can compare the 2-level inverter and T-type inverter. So again, you get some advantage in the overall switching losses, overall losses. Okay, in the T-type inverter. Okay, so it provides a controllable path of current between a neutral and inverter output terminal. So these are the two switches which is actually using some switching on and off. It gives a path when it requires to provide a 0 voltage at the pole voltage. So these two switches come into the action. And very importantly, that this turn on of the switching, because why it incurs a lower switching loss, because it uses the half of these two switches, this neutral point clamps to these bidirectional switches uses lower voltage rating. That is the main reason why it is giving actually lower losses compared to your NPC structure or ANPC structure, because the lower reverse recovery charge which is associated with these diodes, anti-parallel diodes, they during turn of time they will have low losses. Okay, that is the main reason the switching losses will be lower compared to the earlier two version of the 3-level inverter. And all these features you'll get in this reference. And basically, this converter is proposed by Professor Kohler and his group in Switzerland, 2010 paper. You will get these references. Okay, so I think I will stop here, and yeah, one more thing is there, flying capacitor. So I am not talk much about it. You already probably know it. So There is another, apart from this clamping technique, it is also possible to get another level by using a flying capacitors. Here, the main difference of the previous topology and this topology is that here neutral point is not getting clamped. You need not to take out this neutral point, but you are using a flying capacitor. Why it's called flying? Because it is flying. I mean, it is not, the reference is not getting tied with any of the DC bus, either positive or negative. So it can retain this voltage if appropriate control mechanism is implemented. So it can retain this desired voltage, and then using that particular voltage, you can use, actually you can get three different levels at the terminal A. Okay, so but the common strategy is that the switching pair SA1 and SA2, the topmost and bottommost, they should be actually complementary switching, and as well this SA2 and SA2 bar, they also having a complementary or inverted gate signals, and four different combinations are possible. So this is one, when you want to have a plus VDC, so you need to switch both these top two switches. When and similarly for the bottom level, you have to switch both the bottom switches. But when you want to get this middle voltage level, so you have two choice. Okay, so one choice is shown here, other choice is not shown in this particular figure, but you have to understand the other choice would be the other two switches, S2 and S4, okay, is to be on, and the bold path is shown. That means that these two switches are on. When these two switches are on, as shown in this figure, your capacitor, and assuming the capacitor, your current direction is outward, your the pole current direction is outward. So at that particular condition, your capacitor, flying capacitor, is getting charged, right? For the same condition, for the same condition. So if you want to discharge these capacitors in order to maintain the voltage balance, so you have to use the other switching combination, that is S2 and S4. Okay, so that the current through this capacitor will change its direction, so it will start discharging. So that way you can able to balance the capacitor. So but this is extra burden for maintaining these capacitors, is extra challenge are involved, but this is also one of the topologies sometimes is used. So yeah, so that is what I said, that voltage redundancies, that is the zero voltage redundancies, can be used for extra degree of freedom for control or optimization purpose. Okay, and these are the basic feature, but the complex is the complex capacitor voltage. Why it is complex? Although not very complex in control strategy, but sometimes depending on the load condition and power factor and transient load condition, this may become complex, but in steady state this may be all right. And obviously you have to deal with the bulky, not only the bulky capacitors, you have to deal with the flying capacitors that has to be pre-charged. That is also another disadvantage. So you cannot simply start the circuit without charging the flying capacitors. That may not work, but you have to first pre-charge and then you have to run the circuit. That is also another disadvantage. Okay, so yeah, so in future, so just I kept this one more slide. I'll try to finish it. So this is the give you the small flavor that what are the present trends are going on. So not only three level, but I'm not talking about this in details because I thought of restricting into three levels, but I just wanted to give you some flavor. So there are more number of levels, industrial and grades. Industry people are also started thinking and having their products already in 5 level or in 7 levels. So these are some of the hybrid structure also possible. So using some different front end and then the edge bridge, using a flying capacitor based, you combine them and then this become a hybrid structure. And that way this circuit is proposed from our lab. So that's what I am trying to show you some of the advantage. If you compare with other existing topologies, this gives a clear advantage. Although the neutral point balancing requirement is there, from this table you can see but there are some other advantages is showing clearly if you compare with the other structures. Okay, so thank you for your interest and patience hearing. I am expecting some questions or from your side. I'll definitely try to address them. So that's all for today's lecture or discussion. So I'll try to address your queries if you have. Do you have any queries till now? I'll share the slides so you'll get all the references. But do you have any doubt which I can readily answer? Or if you have any further doubts, you can, if you have my email ID, you can contact me later. That is also fine. Okay, I'm just, there is an option called unmute all. If you want to verbally say something, you can say.
Thank you very much, sir, for a very nice presentation.
Okay, thank you, ma'am. Okay, you are there. Thanks a lot. But I don't know whether the other participants they have able to enjoy it, what extent they enjoyed it, or they able to understand. They have any queries, I'll be more happy to address those.
Mama katti de. Mama katti de.
Okay, so I think no more queries, so I'll we can stop here, and I'll share the presentation later. So thank you all.